all these degrees together, and the result going to be an even number, quite interesting one. And the result is going to be twice of the total number of the edges. This is the most popular theorem in graph, and we're going to call it the handshaking theorem. Okay, so this is going to be the handshaking theorem. Okay, handshaking theorem. And basically, this is it, the sum of the degrees. The sum of the degrees. The sum of the degrees of the vertices of a graph. Vertices of a graph is equal to twice of the number of the edges, equal to twice the number of edges. Okay, that's fine. So if you like formula, if G is going to be a graph, if G is a graph with n vertices, we can call the vertex V1, V2, up to the Vn. Then the total number, the sigma of the degree of Vi, I equal to the 1 to the n. You know that this sigma means just addition. So it's going to be degree of the first one, degree of V1, plus degree of V2, and plus degree of Vn. If you add all of them together, this is going to be 2e. The total number of, okay, where E is the total number, is going to be the total number of edges. Number of edges. Okay, this is going to be the one. And the reason that it's clear, you see. So when you add these degrees together, so you are adding all the edges that's going to be passing through the vertices. You may think that this sum must be equal to the total number of the edges. But remember, each edge, this is going to be the edge. This edge is passing through two vertices. So when you count the degree of this vertex, you are going to count this one. And at the same time, if you count the degree of the other endpoints, again, you are going to count these edges. So that is why in this total, each vertex is counted twice. So that's why each edge is counting twice. So that's why it's going to be 2e. Okay. And this is going to be, that's why we call it handshake theorem. When you handshake, you see, when you handshake, this is going to be, you have two, it's going to be handshaking between two persons, if you like. So it's going to be considered twice. Okay, that's why they call it handshaking theorem. So the only reason is that if you like the proof is going to be, note that each edge is going to be, is passing through, if you like, in incident, or just passing through two vertices. and so is going to be counted twice in the total number of degrees. Okay, that's going to be the one. So you have this edge. You see, this is going to be the edge E. The edge E would be what? Would be between the VI and the VJ, if you like. So when you count the degree of the VI, you count the E. And when you count the degree of the VJ, you are going to do the same thing. Okay, so that's going to be the handshaking theorem. Any question? Now, the example is going to be a graph would be given to you. You want to confirm it, if you like, consider the following graphs just to confirm it. Okay, the following graphs. Okay, the number one, the first one. The first one is this one. And these are going to be the edges. So that's going to be A, B, C, and D. So if you count the degrees, okay, the degree of A is going to be equal to the 3. The degree of the B is going to be equal to 3. All of them, the degrees are going to be 3. Okay, the degree of the D is also equal to 3. So if you add them together, so the sigma of the degrees, I from 1 to 4, if you like, is going to be 3 plus 3 plus 3 plus 3, which is going to be equal to the 12. 12 is 2 times 6. 2 times 6, as you can see, 1, 2, 3, 4, 5, 6. So the E, the total number of the edges, is equal to the 6. So the degree of the VIs, I from 1 to 4 is going to be 2, just to get the confirmation. Okay, any question? Sometimes your graph may have a loop, so you've got to be careful when you want to consider the degrees. Each loop would be considered as 2 edges. If you look at this one, because you have some of them in your assignment, just give you one to make sure you know how to do it. Consider this graph. This is the one. And there is a loop here. Okay, so the vertices are going to be the V1 over here, the V2. Okay, and that's the V3 and the V4. Okay, now the edges, you have the E1 here. Okay, this loop would be considered as one edge. So this is the way I call it. I call this one E2. Then I call this one E3. And I have the E4 and the E5. Okay, but I have one edge, one loop. This loop would be considered as one edge. Okay, would be, we have the loop of the E6. Okay, so what we are going to do is going to be, so as you can see, the number of the edges is going to be equal to the 6. I consider one loop as one edge. And then if you consider the degrees, the degree of the V1, okay, degree of the V1 is equal to 2. Degree of the V3 is equal to 3. and the degree of the V4 is equal to 3 again. Okay, to go to here. But the degree of the V2, you see the V2, degree of the V2, you have a 1, 2. So we consider the loop as a 2, if you like. One coming and one going, if you like. Otherwise, this formula is not going to be satisfied. So the degree of the 4 would be equal to the 4. So each loop we consider twice, if you like, when you counted the number of the edges passing through the V2. So if you add the degrees together, okay, if you're adding the degrees together, in this case, we have 4. So that's going to be the 2 plus 3 plus 3 plus 4. So that gives you 12. Okay, 12 and 12 again is 2 times 6. So it's going to be considered to be 2e. Okay, so the formula is going to be again satisfied. So if you want the hint for the problem in your book, so you just note that a loop, okay, a loop E6 is counted. A loop is going to be counted twice. Okay, counted twice towards the degree. Okay, twice the degree of its endpoint. Endpoint vertex. Okay, because as we talk about it, each of these edges is going to be counted twice when we add the total of the degrees. So we have to keep this one to get the numbers. Now, this formula would have various consequences, and a couple of questions that we have are going to be related to these consequences that we're going to have. The first thing is the total number of the degrees of the vertices in a given graph is going to be an even number. So one problem that you have in your book is several of these problems. A set of numbers are given to you and they ask you whether we can have a graph with the following degrees. So simply you add them together and the result must be an even number, okay? So this conclusion would work out for the problems that we have, okay? So the remark is going to be, okay? So the first remark is, the first one is the sum. Okay, the sum of degrees. The sum of degrees in any graph. In any graph is an even number. Okay, this is one conclusion that we're going to have, very important one. The other one is more interesting. You see, when we get these degrees, some of them are even numbers, some of them are odd numbers. This even and the even would cancel out if you like. So you have some odd numbers that if you add them together, they must be also even. You know that if you have a group of odd numbers, and if you add them together to get an even number, if you add two odd numbers together, the result is going to be even. So if you want to add the number of the odd numbers to get an even numbers, the number of the vertices must be even. Okay, let me just write it down, then I explain it again. You see, that's interesting. The number of vertices. It's one of the problem in your book. The number of the vertices with odd degrees must be even in a graph. In a graph is an even number. Number of the vertices with the odd degree. So this means in a given graph, for example, you cannot have three vertices whose degrees are 5. Because 5 is an odd number, you have to make it so that you get an even sum, if you like. So if you add the 3 odd numbers, 3 5s would be 15. 15 is an odd number. Okay, I'll give you the proof for this. Okay, so you know it. They may ask you to prove it. Okay, this is it. If you like, the proof of the first one is clear, but we are going to write it again. Proof the first one, and there you are. You know that. Note that it's the one that we already proved. Okay, if G is a graph, it's going to be a graph with n vertices. With n vertices, I have to label the vertices v1 and v2 up to the vn. Then the total number of the degrees, I equal to the 1 to the n, is 2e. That's it. Is an even number. Okay, is even. That's the proof of the first one. Okay, by the handshaking theorem, that is going to be the result. Any question? The second one, we have to give just a little bit more to get it. Now, how are we going to prove the second one? So we are going to divide the vertices in two parts, the one with the odd degrees and the one with the even degrees. Okay, so for the second part, suppose V1, V2, up to somewhere, up to the Vk. These are R vertices with odd degrees. Okay. So the rest would have even degrees. Then this is what you have. And remember, the total number is going to be, so what we're going to have, let's see, look at this one. You write the degree of the V1, V2, up to the Vk. These are the ones they are all odd numbers. The rest, degree of the Vk plus 1. Okay, plus that to get the degree of the Vn. These are even. So the result is 2e. Look at what you have. This is an even number. Okay, so this is going to be even. 2k1, for example, if you like formulas. Okay, these are going to be even. Over here, these are all even numbers. Okay, you know that when you add the even numbers together, the result's going to be even all the time. So this is also even number. This is going to be even. Okay, these are going to be even. So what we can do is, we can call this one, if you like, call this one 2t. Now, if you subtract it, you see, so the degree of the V1 plus the degree of the V2 up to the Vk is going to be equal to the what? Equal to the 2e minus 2t. So this is even. Okay. So this must be even too. And you know that these are all what? A number of the odd numbers. So if you want this total of the odd numbers to be even, the number k, okay, k must be, so this would be also even. So k must be an even number. Must be an even number. Okay, it's all clear really. You don't have to write it down. and to get these numbers. Okay, so if you have vertices in a given graph, you divide them into two parts. The one whose degrees is even and the one whose degrees is odd. So in your total, you break them in two groups. Groups with the odd degrees, group with the even degrees. But here is also even, that give you even. So you have a couple of odd numbers. You want to add them together to get even numbers. So the number of the time that you are going to add them together must be even number. 5 and 5 would be 10, but 5 plus 5 plus 5 is 15, is odd. So that give you this theorem. These are going to be used if you are going to be, pure graph theories really. But you have, the assembly that we have are going to be of this format, and we give you one of them. Okay, any question? That's how we're going to use it. It's very easy, but make sure you explain it for us on the test. I give one question regarding this type of ideas. There you are. Question is going to be easy. So the question is this one. Is there a graph? Is there a graph? Is there a graph with 10 vertices? 10 vertices of the following degrees. Degrees are 1, 1, 2, 2, 2, 3, 4, 4, 4, and 6. There you are. There are two different ways to do it. One of them is add all these numbers together. Remember, these are the degrees of the vertices. If the sum is an even number, it's going to be a graph. If it's not going to be an even number, you know that this is not going to be possible, because that's the first condition that you have. Okay, so the solution is simply add them together. Okay, say the sigma of degrees is 1 plus 1, 2, 2, 2, 3, 4, 4, 4, and 6. What's it total? Okay, that's going to be 2, 4, 6, 8, 11, 15, 19, 23, 29. 29. 29 is an odd number. Is an odd number. That's the contrary to the what? To that handshaking theorem that we're going to have. Okay, and then you're done. So the answer is going to be no. If you like, you can explain it that the sum of degrees, the sum of degrees must be, must be even. And do that. Any question? The other way to do is, just check the number of the odd. You see, the degrees with the vertices with the odd degree, 1, 2, 3. You know that the number of the vertices with the odd degrees must be even number. You have only 3. You can't do it. Okay, so each method would be fine. Question? This is another one. Another one is this one. In a graph of 15 people. In a graph of 15 people, is it possible? Is it possible for each person? Is it possible for each person? For each person? Each person to have exactly to have exactly 3 friends? Okay, we want to explain it, of course. Explain your, your any suggestion. Because at the graph of 15 people, you can consider 15 vertices, okay? And if they are going to be friends, they are going to be neighbor of each other. You connect them together, okay? You connect them together if they are friends. And you're not going to connect them together if they are not friends. So in this case, when you want to have, if you want to have 3 friends, means the degree of the vertex exactly 3 friends. So it's like having a graph with 15 vertices, okay, 15 vertices, such that the degree of vertex, each vertex is 3. Okay, degree is going to be equal. So 3 is an odd number. So since the 3 are an odd number, remember the total number of these are all odd numbers. So if you add them together, you must get an even number. So it's going to be only possible if the number of the odd degree is going to be an even, but you have 15 people. So in that case, it's not possible. Okay, these are just add them together. Solution. So they are going to be friends. Okay, if there is going to be, okay, if they are going to be connected to each other. So this is going to be your friendship graph, if you like. So we're going to consider the graph. Suppose G is a graph. G is a graph with what? With 15 vertices. With 15 vertices. Whose degree? Okay, with degrees. With degrees. Okay, equal to, a degree is going to be equal to 3. So this is what we have. What's going to be the sum of the degrees? So the sum of the degrees, all of them together, VI, I from 1 to 15, you add them together, it's going to be 3 plus 3 plus 3, 15 times. You said it's going to be 15 times. And you know that if you add it 15 times together, that gives you 45. 45 is odd, which is not possible. Okay, so the answer would be no. And there are different type of the idea, puzzles, game, to just picking the step of, there is a problem that say that an odd person want to have an odd party with the odd number of the people in which they know odd number of the people in that, in that party. Is it possible, an odd person invite odd number of the people to an odd party in which each person will be familiar, will be friends with odd number of the people in the party. It's the same thing, it's not possible because the number of the odd degrees must be even. But anyway, that was the handshaking theorem. Any question? So don't be surprised. You have a list of these type of problems, and this is the way you're going to answer it. And you may get one of them. There are some special graph, especially 2, that we use most of the time. So we're going to introduce those and then be done. And we can get those problems of the review one. The best type of graph are complete graph. These are going to be expanded, if you take a course in graph theory, these are going to be the foundation, but we just mentioning some of them that you may have to use. Complete graph. Okay, what's a complete graph? A graph is going to be complete if every vertex is connected to the rest of the paper, okay? Or a graph is complete if each 2 vertices in a graph connected to each other, or they are going to be adjacent to each other. Okay, that's the best part, the best type of graph. So a graph is complete. Graph is complete if each vertex is connected, is going to be connected to every other vertex. That's it. We call it complete graph. Okay, each vertex is adjacent to the rest. So we have a special notation for it. You must know this notation. The complete. Okay, the complete graph. Complete graph with n vertices. And vertices is denoted by Kn. So you must know that the Kn is a complete graph. You should be able to graph it. We may ask you to draw this graph and get familiar yourself with these. Okay, so the example, this is going to be K1. K1 is the graph with one vertex. This is it. That's a K1. Degree is 0. K2, you have two vertices, and each must be connected to each other. This is it. That's K2. See, the degree of each vertex is going to be just 1. K3, 3 vertex, 1, 2, 3 vertices. Each vertex must be connected to each other, to the rest. That's it. The degree of each vertex is 2, which is 3 minus 1. K4 is popular. K4. A different way to graph it. The bad one is this one. 1, 2, 3, 4. Each vertex must be connected to the others. You see, 1, 2, 3. Again, this one. 1, 2, 3. It's going to be 1, 2, 3, and the 1, 2, 3. The degree of each vertex is 3. But in graph theory, they don't like it to have, you see, you have a intersection here and there is no vertex. If you can redraw it so that you remove this condition, it's going to be called planar graph that we are not going to cover. The best one is this one. You see, if you want to have a planar one, you see 1, 2, 3. That's going to be 1. So 1, 2, 3. This is the famous K4. Okay, they prepare this one, the K4. You see the degree of each graph, the degree of each vertex is 3, K4. And of course, the most popular one is K5. K5, you have 5 degrees and each degrees must be connected to the rest. So this is it, 1, 2, 3, 4, and 5. Connect each vertex to the rest. You see that's going to be 1, 2, 3, 4. You have to do the same for the other. 1, 2, 3, 4. Okay, this one over here, 1, 2, 3, 4. And this one is going to be 1, 2, 3, 4. So that's going to be K5. K5 is popular. You see the one that I did for this one. I just changed it so that these intersections are going to be just vertices. But you can't do with this one. So the K4 is called planar graph, but the K5 is non-planar graph. And this is one of the nice problem in graph theory. It was around for for a long time. And there is a guy, a Polish mathematician, his name is Kotorowski. He proved that the K5 is not going to be planar, means you cannot do it. And then he proved that if the graph is going to be a copy of K5, it's not going to be a planar graph, if you like. So that's that's a theorem in graph theory. There are different puzzles about this one, in everyday life. One popular one is there was a father, if you like. He passed away, and he did have 5 sons, and he left them, a farm, a big one. But he said, you can have it if you can divide it into 5 parts with the following conditions. The first condition is each share, each farm, if this is going to be yours, you must be adjacent to your brothers, if you like. So it must be connected to all the other 4. But the second condition was your share of the farm cannot be intersect, okay, or overlap with the other people's shares. So this means you are the neighbor, but you have to draw the farm so that there is not going to be, it's going to be like this one. This is what's intended. But the one that he was interested in, if you put them together, this is one farm, is connected to all the others. But if you want the share of each body to be one piece, you should be able to graph it, redraw it as a planar graph. And according to the Kotorowski one, it's impossible. So that's one of the people make up different things, different puzzle. So to remind this great theorem, okay? But your job is going to be just to get to know them, and when you want to do any question, so get to know the notion. If I say draw K5, K6, you should be able to do it for us. Okay, that's the idea. And there are a couple of popular conclusions that you can use it, or you must know it for the test, for the Kn graph. The first one is, as I did it over here, if you have 5 vertices, the degree of each vertex is 4. 1, 2, 3, 4. You see, 1, 2, 3. So that's one conclusion, which is very nice. You must know it, be able to use it. The degree. Okay, the degree of each vertex of Kn, if you like, is n minus 1. Okay, and it's clear because we know that each vertex is going to be what? Each vertex is adjacent to the rest. So you have n vertices. So when you pick one of them, the leftover is n minus 1. So you are connected to n minus 1 vertices. So the degree, your degree, you have n minus 1 neighbors. Okay, so the degree must be n minus 1. This is one of them. Okay. The other one that you have to know is, the other one is going to be the total number of the vertices, edges. You see, there are n minus 1 vertices passing through one vertex. Okay. So if you want to find the total number of the edges, so n minus 1 passing through each, but you have n. So n times n minus 1 would be the total number of the vertices. But each edge passing through 2 vertex, so this is going to be, this is it. There are n times n minus 1 over 2 edges. edges in Kn. You see, this is n minus 1. You have n vertices. So it's going to be n times n minus 1. But each edge is going to be what? It's counted twice. So divided by 2. Okay, so the number of the edges must be what? N times n minus 1 over 2. You can use these as a fact in the test, but you have to know them. We're going to make up something and we ask you to do it for us. And the third one, coloring number. Remember the coloring number? Look at this one. What is the coloring number for this one? Remember the coloring number would, you are going to color these vertices so that if they are adjacent to each other, they have different colors. Any suggestion? 3. How about this one?
4.
4. Because each vertex is connected to the other one. So what's a coloring number for the Kn?
N.
And that's it. And the reason is, you see, that's it. Each vertex is connected. Okay, each vertex is connected to every other every other vertex. So that's, that's the things that you may have used or to use to get these numbers. Okay, so this is going to be the complete graph. Okay, we have one more to talk about it. Okay, any question? This last one is called bipartite graph. What's bipartite graph? Sometimes you can partition the graph if you like. Bipartite. Okay, bipartite graphs. Okay, so the bipartite graph is going to be, you see you have one graph. You can divide the vertices in 2 parts. You put one part to the right, one portion of the graph, and one part to the left. With the condition that there is not going to be anything connected inside each partition. This means, you see, this is going to be 2 partitions. This is going to be 2 partitions here. If there is going to be any connection, it must be connected from the first group to the other group. Okay, so you partition the vertices in 2 parts. The first part, you see the red one and the black one. Between the vertices in the red, there is no connection. This when the vertices over here, there is no connection. If there is any connection, it must be between the first group and the second group. If you do this one, we call it bipartite graphs. They are very popular in graph theory. Okay, that's going to be the one. So we define it to be what is the bipartite graph. So suppose G is a graph. G is going to be a graph. And V is its vertices. Okay. Vertices, set, if you like. Such that you can partition it. Such that there are 2 subsets. 2 subsets, V1 and V2, with this condition. The V1 and the V2, if you put them together, union of the V2 is going to be V. This means we just partition it. And of course, there is no connection between the V1 and the V2. I mean, they are not going to be overlapped. So we get the vertices, we divide them in two parts. Okay, so we have two subsets, if you like. And this is going to be the case if no two vertices, no two vertices, okay, in V1 or in V2 are going to be adjacent neighbor, okay, adjacent, connected to each other. Then G is called a bipartite graph. Bipartite graph. Okay, so if you can partition it in two parts, two different groups, two different color. The one in the V1, all of them have a red color. The one in the V2, all of them have the blue color. So there is no connection between the reds. There is no connection between the blues. If there is going to be anything, it must be between one red and one blue. If you can do it, that's a bipartite graph, okay? Example. First one. Look at this graph. This one, V1, V2, V3, and the V4. This is a graph G. Let's think about it. Can you partition it into two groups so that the degrees, the vertices in each group, there is no connection. The connection must be between the first group and the second group, or two different color, if you like. Any suggestion? Put them together. Okay, the vertices in two parts. This is it. The red and the blue one. Between the red one, no connection. Between the blue one, no connection. If there is any connection between red and the blue. Any suggestion? How are we going to group them?
Is it V1 and V4 together and then V2 and V3 together?
Excellent, that's it, yes. V1 and the V2, yes, that's it. You see, because this is, let's call this one red. These are going to be the reds, and these are going to be the blues. Okay, and I have used different color, green. You see? There is no connection inside the reds and inside the green. If there is any connection, it's outside this. Okay, so that's it, yes. You see the V1 is the V1 and the V4, and the V2 is the V2 and the V3. That's it. So as you can see, if you put them all together, you get all the vertices, and there is, the intersection is empty, if you like. And so, we can regraph it to say that this is it. So I consider these two. Okay, and I consider these two. So that's going to be bipartite. This is, you can rewrite it, regraph it. The way, you graph it. So G is a bipartite graph. Again, they are going to be popular, in graph theory. Bipartite graph. Okay, but another one is this one. That's a V1, a V2, and a V3. Any suggestion for this one? Divide them in two groups so that if there is any connection, the connection must be outside the group.
V1 by itself and then V2 and V3.
That's it, yes, this is it. We get the V1. So the set V1 is just going to be V1. The set V2 would be just V2 and V3. See, that give you the red. You know, you can use color. This is red, but these are going to be green if you like. You see, there is no connection between the greens or no connection between the blues and between the reds. If there is a connection from one to the other one, it's a two-part, so that would be bipartite one. Okay, question. Now, the reason that we discussed this one is for the what is the complete bipartite graph. You see, the complete graph is the one that each vertex must be connected to all of them, all the rest. But for the bipartite one, these red one cannot be connected to each other. The red one can be connected to the greens. So you are going to have a complete bipartite graph. All the members in the V1 are connected to the V2, vice versa. So all the members in the V1 connected to the V2 and all the members of the V2 connected to the V1. That would be complete, okay, bipartite graph. So complete bipartite graphs. That's it. It's a very popular one. So there you are, a bipartite graph. A bipartite graph G with V equal to V1 union with the V2 is complete. Is complete if each vertex, each red one in V1 is adjacent or connected to all vertices in V2. From the first group, you have to be connected all to the other one, or the other way around, okay, vice versa. And if you like, you repeat it again. Each vertex in V2 is also, it's going to be automatically happen, is also adjacent to all vertices in V1. Okay, G is denoted by famous notation. Is denoted by K, M, comma, N. This means that the first set would have M vertices and the second set would have N vertices. Okay, it's going to be where the number of the vertices in V1 is M and the number of the vertices in V2 is N. We give you now a couple of these and we ask you to graph it really. That's all we need. When you graph it, then you can, find coloring number, okay, different idea, but nothing else. Let's graph the most popular one. Let me give one question on this. No assignment will be collected from this section, you know. So, but we want to finish it because we have to get to the next chapter quickly. Okay, some popular one is, this is it, to see how we graph. A K1, comma 3. The way we graph, it's two parts. You just get the one with the vertex. In the V1, we have only one. You say this is 1. Then you have 3 other side. 1, 2, 3. So on one side, you get all the V1. On the other side, you get all the V2. Remember the condition. Connection between all. You connected each of one group to the other one only. That's it. Remember, you cannot connect these together or connect these together. That's a K13. Any question? What's the coloring number for this one?
2.
2. Very good. Bipartite graph, the coloring number is 2 all the time. Okay, that's it. K22. There is one of them is important that I'm going to just get. Okay, K22, this is it. 2 vertex here, vertices, and 2 here. So from each of the first group to the other. That's it. Again to the others. That is, again, this is your V1, V2. That's K22. Question? We need one more to get to the famous one. K32. K32, 3 on the first one. 1, 2, 3. 2 in the other ones. 2. Connect. That's the first one. Connect. And connect. This is K32. So these 3 are in one set and the other 2 are coming in the other set. Again, coloring number is 3. It's 2. The famous one is this one. We call it utility graphs. Utility graphs because you see this is a 3. This is 3 vertices. We have these 3 homes if you like. You see there's going to be homes. H1, H2, H3. You see each home would need what? Needs the gas, electricity, and water. So each home would have this connection. Okay, and that's going to be the gas, electricity, water, and the gas, electricity, and water. That's the second graph of the Kotorowski that I talked about at K5 and the K33. This question was around for a long time, that can you redraw it? You know that each home, you don't want to these connections to be, okay, intersect each other. So is it possible to redraw this one so that these intersections would be removed? It was proved that no, it's not possible. So in the case of the K33 and the K5, you cannot redraw it so that this intersection would be out. So if you can do it, the graph is planar graph. If you cannot do it, it's a non-planar graph. Kotorowski proved that if you consider any graph you like, that graph is going to be planar, means you can draw it so that the intersection would have the vertices. If it's not a copy of a K33 and a copy of the K5. A copy, you know, there is a formula. There is a expressions that we define what the copy mean. Okay, so that's why his theorem is so important. K5 and K33 is the key, if you like. But anyway, just for your information, we would like you to know that the coloring number of all this graph is going to be 2, of course. In a bipartite graph, the coloring number is going to be 2. Okay. So we are going to elaborate on this one for the next test. But for the quiz, we just give you one question on these ideas. But there are a couple of other things that we talk about later. Okay, so that's almost this section 4.9. I want to go over to review one. I just give you the proof of those because you are going to prove for us using the method of contradiction. Okay, method of contradiction, method of the contrapositive, and the method of the counterexamples. So we give you one question from each. Okay, and we give you 2 from graph. One of them is scheduling the final exam. You have one on the review. I will post a solution for you for all of them. Because that one takes time. Okay, so I show you the solution of the first one on the review, but because I want to get over explain the proof one for you. You see that is going to be your practice quiz question number 1. Remember, a number of the subjects are given to you, and you want to schedule a final exam for us. We have some students who share these, this is psychology, for example, and history or philosophy. So if they share, you are going to connect them together. You have to graph it yourself. You connect them together, okay? If they don't share, you are not going to connect it. Then you have to color it. Okay, you have to color it so that the condition is going to be those who are adjacent should have different colors, okay? In this case, the color would be the day of the exam, okay? Monday. You may call it Monday, Wednesday, etc. So we did it the other day. We just find the degree of each vertex first. Then we list the vertices from the highest degree down. Then we are going to use different color to do it. Okay, I said the first day, I picked the G, which is geography. That's a G. Then you just go on. If these are not going to be adjacent to the G, you can put it here. Otherwise, you need a new color. The G was a special one. Everybody was taking geography, so I couldn't use any other member. So that's why I get the G only. Then we go to the next one. Yes, question, what's question?
Is there multiple ways to do this? Because when I did it, I only got 4 days. I'm not sure if I did something wrong, or is it possible to be able to get less days?
I got 4 days too.
Okay, I'll double check this one because I know that there was a misprint. This is from summer. 4 is correct. 4 is correct. I double check it before I post it, because one of the subjects was missing last time that we did. Okay, but I double check it. Probably 4 is correct. But before I post this one, I double check it again. I remember I missed one of these subjects. I have to double check it. But 4 is correct. Yes, I double check it and get the 4. I don't remember what has happened to this one, but 4 is correct. Yes, 4 is correct. I double check that one. Okay, so I will post this one for you, the correct one, later today. So let's go over a couple of those proofs to see how we're going to write the proof for us. Okay, so that you're not going to miss any points. That is the one that I posted for you. Counterexample are the most popular one. I'll check the number 1 again, then I'll do it, because I remember that there was something wrong with that problem. But I posted 4. I remember that was 4 is probably correct. The subject that I listed, one of them must be different. I'll check it. Okay, so we go to the question number 2. I explained that one for you. Okay, in number 2, they ask for some counterexample. Okay, remember a situation would be given, then you are going to provide a counterexample for us. So the first part, I explain it here. So you can see the problem, but again, the solution is ready. I posted. So this is practice. Okay, so that would be our, and I start grading your test. Probably I try to finish it by tomorrow so that we can have an idea of that one too. Okay, so that's a practice quiz number 2 and the question number 2. We see the question number 2, they ask you to give us, that's the claim. The claim of the first part is that the square, okay, the square root of any integer is irrational, Okay, so you have to give us otherwise if you like. Give us a number whose square root is not irrational. Any suggestion for this one?
4.
4, yes. You say that the radical 4 is equal to 2 and is rational, okay? Don't just say 4 on the test, okay? Just write it down in a brief description so that you know what you did. Okay, that's the first one. You know, 16 is another one, 25 is another one. So you want to reject it, just one example would be enough. So that's part 1. Any question? Part 2, they ask all. So what's part 2? All odd numbers are divisible by 3. All odd numbers are going to be divisible by 3, which is not correct, okay? So you have to give us one number, otherwise. What's a number?
5 is odd and it's not divisible by 3.
Very good. 5 is odd and is not divisible by 3. Divisible by 3. Okay, 5, 7, you know, these are going to be 17. Any question? The next one, so we get one question is probably 4 parts. And you just give us 4 of these ideas. The next one is that if P is if P is an odd, okay, an odd prime number, then P plus 2 is also prime. P plus 2 is prime. So you have to give us something otherwise. Give us a prime number that you rejected. Any suggestion for this one?
7.
7. 7 is a prime number. Yes, solution. 7 is prime. 7 is prime. Okay, but P plus 2, 7 plus 2. 7 plus 4 would be 9. You know that 9 is not prime because it's divisible by 3. It's not prime. Okay, so this is how we're going to take care of that counterexample question. Any question? Read it carefully. It's not going to be something difficult. Okay, just about the lines, about these numbers that we talk about it, and you should be able to do it right away for us. Okay, that's question number 2. Question number 3, prove by contrapositive. Let's see what you should prove. Okay, prove. Again, you have the solutions, but I explain it. Prove using the contraposition. Okay, that's it. Contraposition. Remember, the contraposition means we just recall, if you like, this is what we are going to do. Recall that if P then Q is what? Is equivalent to the not Q implies not P. So what you are going to do for us is you read the expression carefully. You consider this, you know, you want your expression would be if P then Q. So you try to prove not Q implies not P. Okay, so this is your writing again is very important for us. Okay, let's explain one of them. So the first one is again is not going to be anything unusual. You know it, you know the information. If the product, this in fact the only method you can prove this one is contrapositive. If the product of two integers, okay, if the product of two integers, x and y, is odd, okay, is odd, then the claim is both of them must be odd. Then both x and y, okay, are odd. Okay, this is your P then Q. Okay, that's the one. But the thing is that you have to consider the contrapositive and then prove the contrapositive. Okay, so let's see what we have to prove the contrapositive of this argument. Okay, so the proof is going to be, you have to give us that contrapositive. Say, oh, one or I, one should prove that. Remember, this is like, this is going to be, this part is going to be your P and this is going to be your Q, if you like. So you have to give us the not Q implies not P. Any suggestion?
If either X or Y is even.
That's it, yes. You see the negation of the and would be or. So one should prove that if X or Y is even, then what?
When the product of X and Y is even.
Then X times Y is going to be even. You see, very important to put it into the good format or the correct format. Any question? So start with this one. Suppose one of them is even, this is going to be odd, write the definition, and then you're done, okay? So I'm going to suppose, I suppose X is even and Y is odd, okay? Y is odd. Write the definition of the odd and even. X is even, so there is a K, we call it K1 because we want to use it twice, such that X is 2K1. Okay, that's one. Then Y is odd, so I need another K, I call it K2. K2 such that X is equal to the 2K2 plus 1. But what do you want? The product, multiply together. So the conclusion is going to be X times Y is equal to what? Is equal to the 2K1 times it by 2K2 plus 1. Remember, you want to prove this is even. So you need to show that this is of the form of the 2K. So there you are. You consider everything over here, see K1 times 2K2 plus 1 to be K. So that give you what? That give you 2K. So what you proved? You proved that there is a K such that X times Y is equal to the 2K, and that's it. And so X times Y is going to be even. Okay, any question? So nicely, let's give your reason.
Would we end it by saying by contrapositive?
Yeah, very good. Yeah, I'm not done. You are going to write it down by contraposition, by contrapositive law, if you like. Now you express that idea that if X times Y is odd, okay, it's going to be is odd, then X and Y are odd. X and Y, all of them are going to be odd. Okay, so this is how you take care of this contrapositive part. Okay, the second part, I write the proof for you. Okay, that's going to be the one. It's going to be similar to the argument that we talk about it so that you will see it. because I want to give you one of those. The contradiction one, most of them is the one that we did, okay? So that was number 3, just one from the other group, just to explain it. Most of them are the one that we prove and we just change the numbers. Yes, question?
Quick, for number 3, problem C,
Problem C.
could you explain kind of how you would negate the second part? Then at least, would it be both of the numbers are less than, or are greater than or equal to 10?
No. This is the one. Can you see it? You see what you want to prove? That you want to prove what? This is going to be the result. You want to prove that if the sum of two real numbers is less than 20, at least one of them is going to be less than 10, okay? So this is what you have. If x plus y is less than 20, then x is less than 10 or y is less than 10. When we say at least, this is it. Then the contrapositive would be what? The other way around. The other way around is if both of them. If x is greater than 10 and y is greater than 10, then you want to prove that x plus y is greater than or equal to 20. Okay? Then you know that just algebra, nothing else. As soon as you assume that x is greater than 10 and y is greater than 10, you add them together. In algebra, we can add x plus y, 10 plus 10. So x plus y greater than or equal to 20, I do that. So the important part is how we're going to translate it, if you like. How you change it to that. At least means just either, just one of them, at least one, okay? So that is the part C. This is the one I talk about. I gave it to the test. You know, some people, you know, they get confused, especially with the second part. They try to give me an example. No, x is bigger than 10 and y is bigger than 10. So you add them together. X plus y is bigger than 20, and then you that. Okay, so you know, post this one for you so they can see it. So let me just explain that part. The contra one, there is one of them is, I think, related to the graph. Okay, you see we have the part 4, we have quite a lot, proved by contradiction. We almost did all of them. If you compare it with your, okay, your lecture notes, you will see that I did all of them. The first one is, you see, the other one is, let me just show you the first one. This first one is no specific number. Just want to make sure the way you write it down is you are all right. Otherwise, the rest I did it for during the lecture. Okay, just check it and I write the proof again for you. You see this first one, some people have difficulty to do this one. It's a kind of theorem. All the other follows from this one, but we want to have it in general. You see what you want to prove? If R is a rational number. Rational number. And X is irrational. X is irrational. Irrational, then R plus X and R times X are irrational. You see, in the other part, R is equal to 10, then X is equal to radical 2. So all the others are follows. But the method for proving is going to be, okay, the method contradiction. So for the contradiction, I'm going to prove one of them. See, the proof is going to be, you suppose not, suppose not, suppose not. What does it mean? This means assume. Otherwise, assume that R is rational, R is rational, and X is irrational, is irrational, but R plus X, for example, is a rational number. Okay, is rational. as we did it for the other. Just write the definition of the rational number. What does it mean? Definition of rational numbers, there is an A.
Would it be r plus x or r times x?
No, no, I do it one by one.
Oh, okay.
It's two different problems. You have to do it twice. Okay, you have to do it twice, two different problems. Okay, so we assume that there is an A. You have to repeat this one for the other. I do the sum. Okay, there is an A, there is a B, of course, not equal to the 0. Okay, such that what? Such that R plus X is equal to the A over B. See, that's the idea. Remember, in the case of the radical 2 that we did, we isolate the irrational number. Isolate the irrational number. X is the irrational number. Okay, R is like 10, 2, 3. So you do the same thing. So you isolate, it's going to be X equal to, this is going to be A over B, this is going to be R. You see, A over B is a rational number. R is a rational number. We talk about it. The difference rational number. You can find the common denominator if you like. If you like, you can go on one more step. So rewrite it as common denominator would be B. And this is going to be what? A minus R times B. Okay, so you have the X is equal to the A minus R B over B. Now, this is a rational number, because the top is all rationals. B must be a non-zero number, which is the case. But this is irrational. Irrational. So we get a conclusion. Okay, it's like the radical 2 and the 10 that we did before, but you must make sure that you isolate the correct one. You isolate the irrational number, which is X. So a rational number equal to the irrational? No, never. So by contradiction, R plus X is irrational. And you're done. Okay, just make sure to put them nicely together. Okay, nice together, just go on, get this one as a fraction. The term to the right is fraction, the term to the left, radical 2, radical 3, pi. So that's how you get the conclusion. Okay, any question? And you just do the R times X for yourself. I completed that solution. You have to repeat it again. You see this is going to be R times X is A over B. Then this time you divide. Again, we get a contradiction because rational number and the irrational. Okay, for the rest, we just give you numbers. Okay, you have the 10, radical 2, radical 3. So the rest would follow right away. But I will post the solution for you by tonight, later tonight. I'll have a class. I finish at 4, then I put this together. I have to check that graph that we talk about, but I'm sure that it's 4, unless there is a misprint over there. Okay, that's it. Any question? So the graph theory one is easy, okay, but we give you 6 questions, 4 from the non-graph one and 2 from the graph. Make it 6 to make sure you're ready for the next test. Okay, question? Have a good day. If you have anything when I post it, just email me. And the assignment is already posted, nothing from 4.9. Okay, make sure your assignment is going to be on time and we put them together to get your points. Okay, have a good one and see you on Wednesday. We give you the quiz and a lecture. Okay, that's one. Bye-bye.
Have a good one, Professor.
Bye-bye.
I'm going to see you Wednesday.
Bye.
Bye.
Thank you. Take care. Bye-bye.